Hi there! Welcome to the Thin Films and Electronic Materials group led by Professor Sumit Agarwal here at Mainz. We are a diverse group focuses on various aspects of the synthesis, characterization, and also applications of ultra-thin films in semiconductor processing. Our group has two components. Half of the group are working on thin film growth through atomic layer deposition and atomic layer etching. Both techniques are extremely important in the continuous downscaling of semiconductor devices. The other half of the group focuses on different aspects of high-efficiency crystalline silicon solar cells through collaboration with the National Renewable Energy Laboratory under Dr. Paul Stratton's. We make solar cells from bulk silicon wafers to actual devices that can generate electricity. So now, we would like to take all of you on a virtual lab tour.
Hello everyone, welcome to the Atomic Layer Processing Lab at the Colorado School of Mines. Our research is primarily focused on thin films through atomic layer deposition and atomic layer etching for microelectronics. The reactor seen here is a custom-built reactor by the graduate students. It consists of an ALD chamber connected to a turbomolecular pump, which can go to low pressures as low as 10⁻⁻⁶ torrs. The reactor is also connected to a RF power source for generating plasma. The reactor is set up with an in-situ FTIR setup for real-time monitoring of surfaces before and after the reaction. All the gases and the reactant delivery lines through vapor phase are through pneumatically activated valves, which are controlled by LabVIEW.
Hello everyone, this is Matt standing in the Diagnostic Development Laboratory where we have many unique measurement tools. We have electroluminescence, photoluminescence, lock-in thermography, and capacitance voltage measurement tools. But today I'm going to be discussing with you one of our most important tools. This is our laser scriber, where we begin with pure crystalline silicon wafers and then scribe them using this green laser in order to cut them into numerous 30 by 50 millimeter pieces. Here we have that same wafer after laser scribing, where we can see 11 rectangular pieces that will eventually go on to become their own solar cells. Hello everyone. I'm here at one of our numerous wet benches at NREL, about to perform the next step in the process after laser scribing of our samples. We're going to be doing potassium hydroxide etching of the surface of the samples in order to clean off any impurities that might be at the surface of the sample. Now this is a pretty simple process where all we really need to do is take the samples out of the DI water after rinsing them for a little while, and then move them into the potassium hydroxide solution and begin the sonication. The bubbles we see here are actually the potassium hydroxide reacting with the surface of the silicon in order to remove several microns of silicon to reach the cleaner silicon underneath it.
Hello everyone, this is Kejun speaking, and I'm a third-year Ph.D. student in our group, and I will now be taking you to one of our clean rooms for processing ultra-pure silicon samples that will be ultimately made into a device. Right here is the grounding room to one of our clean room, and so here we have coveralls, shoe covers, hair nets, and everything else.
Hello everybody, my name is Caroline. I'm a third-year PhD student in Dr. Agarwal's group, and I get to do my research at the National Renewable Energy Lab. What I'm gonna show you here is our clean room lab, or I guess one of them, but this is a very resourceful one, so I actually have a lot of things to show here. So let's start with this wet bench. This wet bench, it's where we do most of our silicon cleaning. So we do various sorts of chemical etching that allow us to remove most impurities from the surface of the wafer. By this wall we have 8 tube furnaces, where we are able to run various types of thermal processing, such as silicon oxidation or crystallization, and then we use a computer to monitor the activity of those tubes. With this control, we are able to flow different types of gases, control the ramp rate of heating of the tube, and so on. So let's get to this other section of the lab. This is our UV ozone tool, and we also use it for cleaning purposes. But instead of wet chemistry, this is dry. We use ozone, which is an effective way of removing organic impurities from the silicon wafer. This is our reactive ion etching tool, and as the name implies, we use it to remove material from our samples. For example, silicon nitrides, silicon oxides, or even silicon itself can be etched with this tool. Here, by this computer, we have a photoconductor's decay tool that we use to take a lot of important measurements about our samples. This is what I had for this lab. I hope you guys enjoyed it.
Okay, now we're in another room inside the clean room, and this is a multi-user lab space. And right through that door, Caroline just showed you the lab where we do most of our processings. And right now, I want to show you another very cool system that we use, and it is right here, to deposit metal contacts onto our samples. So this metal evaporation tool operates under very low pressure, and it evaporates various metals such as silver, titanium, and also aluminum under high temperature. So right here is the process chamber, and we also have some masks and also platens to hold down the samples stored in this nitrogen box. And over here, we have the main control system, which features a very nice touchscreen display to control the status of various components such as pumps, gate locations, and so on. Right here, we can also control the speed of the deposition, and over here, we have the readout for the main chamber pressure and also the process chamber pressure. Now let's see some characterization tools we use. This room has a lot of X-ray characterization equipment, and there are 3 XRF here. So here is 1 XRF, and there are 2 XRD over here. And this is a solar simulator where we have UV radiation light. And so let's go over here. This is the system that I'm using for XRD. And as you can see, I'm currently running a scan. Okay, so now let's open up the chamber. Here we have our setup. So right here we have our X-ray source with a copper K alpha radiation. And right here we have a slit which we can control the size of the beam. And then right here we have our silicon sample, which is mounted vertically on the stage. And here we have our detector, which during the experiment, this will rotate, and when it satisfies the Bragg's law, or when it has constructive interference, we'll see the typical peaks we see in an XRD spectrum.
Hi everybody, my name is Abigial Meyer, and I am a 4th year graduate student working in Dr. Agarwal's lab. I mainly work at the National Renewable Energy Laboratory, and today I'm going to be talking to you about electron paramagnetic resonance, which is what I mainly do on the NRL campus.
So electron paramagnetic resonance, or EPR, basically uses magnetic and electric fields to characterize defects in substances. These substances can be solid, liquid, powders, etc. In our case, we're characterizing silicon, which is in the chamber right now. And so what happens is a constant magnetic field is applied to the sample, as well as a scanned, ever-increasing magnetic field. This EPR setup is quite unique because it can go to cryogenic temperatures. So typically what I run at is about 6 Kelvin. And so at 6 Kelvin, we're able to study this boron-doped Czochralski silicon because
the boron acceptors are frozen out at that temperature. So this is what electron paramagnetic resonance data looks like when you're taking it. We're plotting an EPR intensity on the y-axis as a function of magnetic field on the x-axis. And we can see that there is a EPR signature characterized by an increase and a decrease in EPR intensity in the middle of the screen. And where the inflection point is, where the cursor is going through right about now, is called the G value. And that G value can tell us a lot about the electronic structure and the electronic environment of defects found in the crystalline silicon bulk.
This is the Surf Solarium, and it is one of my favorite places here at NREL. As you can see above you, we have many flags representing the diversity of NREL employees, and at the very end, there is a kitchen area where people can heat up their lunch. But also you can just come here for a nice break from your day-to-day life, and also just to enjoy some Colorado sunshine. Thanks for watching. I hope you all enjoyed it, and we look forward to seeing you here.